Sang-Youn Kim, who is a professor in Korean University and Education Technology. Today I will present the design of soft haptic actuator based on Plasticized PVC. Actually, the Plasticized PVC has a very special characteristic. Normally, most of EAP, in EAP, when we provide voltage, is stretch it in the horizontal direction and compress the vertical direction. But our material has moved to the angle. According to the voltage, it's act like a mass. So today I will present how can I make some biodetector actuator using the Plasticized PVC. And then yesterday I heard that from someone I was a bad guy yesterday. The reason is that I have no chance to introduce myself. So I insert my introduction page. My name is Sang-Youn, and the interesting thing is I'm in the computer science division. I'm a material scientist, and then someone sent a sample to me. It is a good sample to introduce yourself. So that the sentence begin to study haptics about 20 years ago. It's very nice for me, so I copied it. So my interest in haptic actuator and haptic sensor and virtual reality and augmented reality like that. So, okay, so have you ever enjoyed seeing this movie? The title is it's a Minority Report. There are three girls who can see the future in dreams. So the dream is saved to the PC. So whenever policeman or the government officer investigate the future crime, they can investigate. They can find some dreams. So there is a scene find the future crime. He wear a glove, so maybe he can sense a haptic sensation. But most glove is very soft and very flexible. However, the most actuator are too rigid, too fully embedded into the haptic glove. You know that actuator. And then I participate the CES 2019. I can see a lot of very special display. The first one is it's a flexible display made by Royal. And then the right one is a rollable display made by LG. So how can we insert the rigid display, rigid actuator to the flexible and soft actuator, soft display? So we focused on the flexible and soft haptic actuator. The cube said that there are two major electroactive polymer. Yeah, the electroactive polymer is very attractive material for making the soft actuator, you know that. But there are two major electroactive polymer. First one is the ionic EAP. The ionic EAP, in ionic EAP, the input voltage induced a synthetic volume change in polyelectrolyte, where the migration of solvent happened. So the actuator is bad. But polyelectrolyte is vulnerable to solvent evaporation. Furthermore, the vibration force is too weak to stimulate the human chemical receptor. Many people focus on the non-ionic EAP. It is consists of thin dielectric or piezo film like that, the sandwiched between two compliant electrodes. Under voltage input, the non-ionic EAP expanded in final direction and compressed in thickness direction. And as soon as we remove the voltage, it returns to its original shape very quickly. So it can create a strong vibration. But the problem is the pre-strain should be applied to the non-ionic EAP, and then a flexible or stretchable electrode are required to operate the non-ionic EAP. Anyway, we first we'd like to solve haptic actuator. So many years ago, we bought some VHB made by 3M and made some actuator. But actuator's performance is not so good. So we'd like to improve the VHB. So first, we prepared the 3M, the VHB, whose thickness is about 1 millimeter, and then we stretched VHB to the 1600% to the stretching tool like that. And then we apply the stretched VHB to the rectangular frame, and we spray the solution, the TMA solution, to the both sides of the stretched VHB, and then insert it into the vacuum chamber, and then finally we can get it's very transparent and soft vibration film. As I said before, the weak point is it needs a stretchable electrode. So we consider that how can we make a stretchable electrode? So we studied about that, and hydrogel is the best performance. So we made the hydrogel. And then we apply the hydrogel to on the surface of both sides of the both surface of the IPM VHB, and then we provide voltage. We can create the vibration with this kind of haptic actuator. And here is the example movie clip for a haptic actuator. You can see it's very transparent and it has good stretchability. And then we construct a special the experimental setup and provide the voltage with some frequency. As we change the frequency, we can feel this haptic sensation, and we increase the voltage. The magnitude of vibration increased. The resonance frequency is about 200 hertz maybe.
Do you measure with LDV?
Yeah. And as I said before, the problem is the stretchable electrode. So we studied some material. The reason is that we really want to get a soft actuator without any flexible and stretchable electrode. So it can create a strong vibration force, and it has very high flexibility. So based on the study, we found that the plasticized PVC does not need any flexible electrode. So we improve the plasticized PVC. So we developed the non-ionic and eco-friendly plasticized PVC, what we called it ePVC gel. The ePVC gel can be made by synthesizing polyvinyl chloride and acetylbutyl citrate. We call it the ATBC. We'd like to know the haptic. We'd like to know the actuation performance as soon as possible. So we made this bending actuator like that. Here is the plus-size PVC, and there is a dipole. If we provide voltage, this dipole moves to the anode with dragging this kind of the PVC chains. So the actuator bend. Here is the movie clip. Yeah. You can see that actuator is very transparent. The transparency is about more than 90%. We can make the plus side PVC like that. First, we pour the PVC powder and ATBC solution into the THF and stir it. And pour the PVC ATBC solution to the beaker and dry. So finally, we can get this kind of plus side PVC gel. And yeah, so we're ready to make the soft vibroprotector actuator. So we designed the soft vibroprotector actuator like that. Here is the EPVC gel, and this one is the electrode. And whenever we provide voltage, it moves to the anode like that. But one of the most important things is to maximize the displacement. So we considered that how can we maximize the displacement. So we redesigned the EPVC gel like this wave shape. Okay, here is the fabrication process of the wave shape. Can you hear my voice? Okay. So we are
recording your voice.
Oh, really? So how can I?
It's muted. You're making great actually.
Yeah, I introduce myself. Here is a fabrication process of our actuator. First, PVC powder and ATBC solution to the THF and stir it. And we pour the solution into waveform Teflon dish. And then drying. And finally, we can get this PVC gel. And then we design a structure. Our actuator consists of 4 layers. First one is the upper layer and wave shape EPVC gel and adhesive tape, and lower layer. The upper layer is composed of the flexible bridge act as a spring, an actuation part, and flexible supporter. And this flexible supporter is attached to the this part, and then finally we get this design. This one is a cross-sectional view of our actuator. Yeah, here is the upper layer and flexible bridge like a spring, and EPVC gel and lower layer. This structure has great advantage for making the haptic vibroprotector actuator. The reason is that two energies are merged in the actuator. The first energy is caused by the electric field induced deformation. It's their own characteristic of the EPVC gel moved to the anode, like I said before. And then, due to the parallel electrode, there is electrostatic force. So we can maximize the vibroprotector performance. And the weight ratio is another important factor. The reasons that the dielectric property and mechanical property of the actuator depends on the weight ratio. So we prepared the 5 EPV scale sample with same size but different weight ratio PVC and ATPC plasticizer. So 1:1 and 1:3 and 1:5, 1:7, and 1:9. So 1:5 has the best performance. And here is a movie clip of our actuator. Our actuator is very flexible. And then, to measure the vibration performance, we use the range vibrometer. And Sang-Youn test our actuator, so he know our actuation performance, and you know about it. He know about that. Yeah, you can see that according to the voltage, AC voltage, we can create a lot of haptic sensation, and then we are really wondering about the curved object. When we attach our actuator to curved object, the performance here. Same range vibrometer used. We can yeah, there is a result, and smaller curvature still work. So yeah, our actuator is well operated.
Where do we apply the voltage? Where exactly do we apply the voltage? We apply it to the anode?
It's a voltage.
Yes, where do we apply it?
It's
I think I missed that one.
oh. Okay, we attach the this is the electrode. Here is the electrode, and we provide voltage here and here. And this is the cathode, and this one is the anode. So the provide voltage, it goes to down like that. And the amplitude of voltage is very high. It's still high. It's about 1 kilovolts. However, the current consumption is so low. It's below the 10 micron, the ampere. So the total power consumption is lower than the conventional ERM or ARA. And the dielectric property is also the important factor. So you know that the dielectric property can be divided into 2 components. First one is the dielectric constant, and second one is the dielectric loss. So many people focus on the dielectric constant, but the dielectric loss is also important. The reason is that the dielectric constant is related to the energy. However, the dielectric loss is dissipation of energy. It's not stored but dissipated in the actuator. So we'd like to decrease the dielectric loss of the actuator. So we insert the silicon dioxide nanoparticle to the plasticized EPVC gel and tested it. So 1 to 0.1, the weight ratio has the best performance. So, and the structure is another important factor. So, as I said before, whenever we provide voltage, this dipole goes to anode. We're dragging the PV chain, so like that. But the deformation mainly occurs this point. The most energy at this point are disappear. So we need to concentrate the electric power on the ridge. So we redesigned the actuator like that. First, we prepare the polyimide film with thickness is about 200 micrometer. And then we apply the aluminum masking. And then we sputtered gold to the mask and the polyimide film. By removing the mask, we can get the polyimide film with the patterned electrode. After that, we have to make this spring and using the laser coating, and then we put the PVC gel onto the gold sputter polyimide film and attach the film to on the surface of the PVC gel like that, and finally we can get the actuator. And here is the actuator, and this one is the oscillation behavior. So our actuator has a good performance. And then our material is very transparent. So I'd like to know the other applications. So we thought. At the time, the Q suggests to me, how about making a lens? So wow, that is a great idea. So we made a lens. We prepared the IQ glass, and then we put the PVC gel on the IQ glass and push the this CU electrode with circular shape and push the PVC gel with that circular electrode. When we provide voltage, the dipole moves to the anode, and the middle part goes down. So according to the voltage, we can change the focal length. So here is the example of our lens. Okay. And then, yeah, there is the people the right side, that is PVC gel. It's very transparent, isn't it? And that PVC gel is very stretchable and transparent.
What's the thickness?
It's about 800 micrometer. And then we attached our lens to the cell phone. Here is a marker, and the focal length is changed from here to there. Actually, frankly speaking, our actuator is very transparent, but those during the capturing that movie clip by the student touch the surface of the lens, so it's just a little bit. Anyway, and then nowadays we are making a transparent and stretchable the sensor. It's pressure and it's a stretchable sensor, a strain sensor. So we are composing a paper using this sensor. As heat press the sensor, the capacitance changes. And yeah, the Guillaume said before that during his talk, we'd like to change the stiffness. So we are making some magneto-realistic elastomer. And this one is ongoing project with Q. It's very soft. And here is a permanent magnet. And we attached the MRE, magnetic reverse elastomer, is become very stiff. Okay, so I have a plan to make a haptic glove with electroactive polymer, where we can create kinesthetic sensation and tactile sensation. And then the future, maybe we can have a shape changing device. We have a plan to make a shape changing device with electroactive polymer. So let's consider the situation. There is your cell phone, and there is camera, and then the cell phone recognize you. They said the hello like that. Hey, hello. So it's very interesting. We are making this shape changing device with electroactive polymer. Okay.